One blockade, for example, that's here. And because like the particle has surface charge, and then under certain voltage, the faster, if it has higher voltage, surface charge, under certain voltage, it will passing the pole quicker. So, which means the duration time is shorter. By this mechanism, so it's used to detect the surface charge of the EVs. So, means the TRPS can use the nanopore to detect the size, concentration, and zeta potential of the EV particles. Zeta potential is a very important character because it assesses the stability of the EVs in the solution. Because when later, if you're making a drug, EV drug, and if the zeta potential is very low, which means it's not stable in the solution. For example, it aggregates in maybe just 1 day, 2 days. That is not the customer want. So which means you need to measure the zeta potential and maintain, that is maintain about like the larger than 30 millivolts. But we know that if the value is larger than 30 millivolts, which means it is stable in the solution. For example, if it's just 10 millivolts, which means it's just it will form aggregate very soon, maybe in half a day, 1 day. So that's the device function used to measure the size, concentration, and the zeta potential. And as this mentioned, the blockade magnitude is proportional to the volume, the size of the particles, and the frequency can be like converted into the particle concentrations. And the duration is related to the surface charge. Because some researchers, they will modify their EVs to add some proteins, and then all conjugated with like a RNA stuff on some. That one will change the zeta potential of it. You need to test the zeta potential to see whether it's stable in the solutions. And you may ask, how this works? Because for the TRPS, it requires another thing, it's calibration particles. The calibration particles have the known size, concentration, and zeta potential. We first measure the calibration particles, get the data set for the calibration particles, and then measure the sample under the same conditions, and then use the base of the calibration particle to calibrate the sample. That's how it gets the actual size, concentration, and zeta potential. And the TRPS can be used for a lot of things, not only the EV measurement, and also it can be used for like virus and the LNP. So we have a customer doing, for example, the messenger RNA vaccination is conjugated with the LNP. They can also use for the LNP stuff, and also or like a drug carrier for the liposome stuff, and also the virus, some of the lentivirus, they can also use for that. And also it can use for, because it measures the single particle passing through nanopore. It can also analyze the particle aggregation. For example, when we make a drug, the formulation, we need to test whether it will easy to form the aggregation. Because the aggregation, if you inject into human body, that's very terrible, very serious side effect. So the TRPS can also use to measure the particle aggregations. And also it can use for industry control. And this is non-relevant to the biologic. Some of the gold particles or the polystyrene, and also can measure like microplastic. Some like for example, microplastic in the water. So we know microplastic is harm to the human body, right? And also it can use in the cosmetic and the semiconductor area. So it's measured. The only requirement is the particle, if it can be dissolved or form a stable solutions in the electrolyte, TRPS can measure that one. But if it cannot be stable in the electrolyte, it's hard to measure. For example, we need the particle to stabilize in the measuring electrolyte for at least half an hour. But for the biologics, it's usually very stable in the measuring electrolyte. The measuring electrolyte is just the PBS or sodium chloride, so it depends on which one you want to use. And you may ask, so this measures the nanoparticles passing through nanopore, whether large particles will block the nanopore? Yes, that's the part of the troubleshooting procedure. So we provide guidelines for how to do the troubleshooting. So the training is mainly about how to unblock a nanopore when the blocked events happen. For example, if some of the sample is not very pure, for example, for example, the UV solution contains like large particles, for example, over 600 nanometers or 700 nanometers, but the whole size of nanopore is around 400 nanometers. So we block the nanopores. So we provide a guideline how to unblock it during the measurement. That's why it's for the training purpose. And let's talk about why it's tunable. So the tunable pore sensing depends on several things. It's the nanopore structure. So the nanopore is so you can have a look. So it's actually a plastic pore. Plastic pore, like it's transparent area, is the nanopore. Don't touch that area. So you can see the forearm of it. When putting on the device, so currently the nanopore is closed because it's manufactured closed, and then when on the device it will extend the structure to open the nanopore. So that's why you see what we mentioned here, the nanopore structure. And for the same particle, the blockade, the DI, is negative proportion to the structure. We can imagine that if we put the hole bigger, so the same particles create the blockade event will be smaller when the nanopore is small, right? So you can see that it's like a negative proportion of it. As to the voltage, for the same particles, if we increase the voltage, and the same particle will create more of the blockade signals. We know that the physical formula is resistance R equal to V divided by I, right? So that's the same thing applied to this one. So it's what increase the voltage and the duration, the blockade of the same particles will increase. And the third one is applied pressure. The applied pressure is to pushing the particles passing through the nanopore quickly, so which means to reduce the time of the measurement. But when the pressure is too high, so the same particles will make less blockade of the same nanopore. We can see it's also negative proportion to it. And we provide a different size of nanopore for different measurement. For example, you see here the NB100, NB150, and NB200. This catalog is mainly used for the UV measurements. And you see we also offer very large pores. Large pores is used for other purposes. For example, some people use. Yeah, so for example, the largest one is NB4000. Its measuring range is around 2000 nanometer to 11 micron. So that one is usually used measuring the cells or the E. coli, so bacteria. And what is important here to adjust the structure and the voltage to make sure the mean blockade of the calibration particles larger than 0.15 nanoamps. This means that the calibration particle have no size. For example, the calibration particle CPC 100, which means it has the mean size of 100 nanometer, and it ranges from 50 nanometer to around 120 nanometers. I ensure that the calibration particles have the mean size of 0.15, ideally 0.2, let's say 0.2 nanoamps, which means that 0.2 mean nanoamps equal to 100 nanometer. And then we can see that the 0.05 nanoamps, which means the lower detection limit is around 40 to 50 nanometers. So by ensuring this way, which is guaranteeing the lower side of the detection limit of the instrument. And also this one RNS, which means the system noise. System noise is the baseline noise, which should be less than 25 picoamps. You see the picoamps is much smaller than the nanoamps. So it's basically very accurate.